Again, without summarizing this information, this doesn't make any sense. I hope you agree. So we have f prime of x, we have f of x, and we have the second derivative. So we start with the values that are given to us for f prime at 0. So I see everything happens at 0, 1, 2, 3, 4. Okay, negative infinity to infinity, 0, 1, 2, 3, 4. F prime of 0 is 0. F prime of 2 is 0. F prime of 4 is 0 as well. So this is done. The first derivative is positive to the left of 0 and between 2 and 4. Done. The first derivative is negative between 0 and 2 and to the right of 4. Done. The second derivative is positive between 1 and 3. Done. And it's negative between to the left of 1 and to the right of 3. Done. So now let's see what the table is telling me. The table is telling me that there is an inflection point here. And then there is an inflection point here because it turns, it's open down, upward, downward, upward, downward. This one tells me that it has to be a local min. I'm sorry, of course I meant max. This tells me that this has to, it looks like a local min. And this looks like a local max. So, or relative max, it doesn't matter. So local max, going up and down. That is very clear. Here's my take on it. There's more than one correct answer. So 0, 1, 2, 3, 4. Opening down till the inflection point at 1. So at 1, 2, 3. So at 1, it has an inflection point. It's opening down, and somewhere at 0 has a maximum. I signify the maximum, so it's very clear. I show that this is an inflection point at 1, at x equals 1. It changes concavity, and it reaches a local minimum at 2. Okay. From opening down to opening up, reaching at a minimum at 2, whatever you want. It doesn't matter. It continues to increase, still opening up till the inflection point at 3, where it changes concavity and it reaches a maximum at 4, and then continues whatever. So I specifically and clearly specified or presented at 0 there is a maximum, at 1 there is an inflection point, at 2 there is a minimum, at 3 there is an inflection point, at 4 is a maximum, and continues to open down. So opening down, then opening up between 1 and 3, and then opening down all the time between 3 and infinity. So this is an example. Is this okay? Any questions? Any questions? What else would you like to review? What else do you have questions on? Study the function on a closed interval, Rolls and mean value theorem, graphing, using the table, L'Hopital's rule, or any other limit. You may find a limit very easily in a different way, or L'Hopital's rule.
Could we do some of L'Hopital's rule, please?
Yes, very good. Would you like to choose? Let me open that.
No, you can choose.
Okay.
I don't have anything in particular.
Okay, so let's go to 4.4. And let's choose more problems from L'Hopital's rule. I mean, from 4.4. As you know, if there is an easier method, why would I choose to use L'Hopital's rule? If there is something easier, I will use that easier thing or method. Okay. So from 8 through 70, find the limit, use L'Hopital's rule where appropriate. If there is a more elementary method, consider using it. So anything you would like to choose, or I'll scroll slowly. You choose, or I will.
You can choose.
Okay. I will choose 16. And I am on page 7. You can choose the next one. So limit as x approaches 0 from x squared over 1 minus cosine x. Good. So this is not a situation in which I have to simplify the function like we had here. Last time we couldn't even plug in. Here I cannot plug in. I have to simplify this into one fraction. Add or subtract these fractions. In this case, subtract. I don't have absolute value. So these are the situations that we encountered in which we couldn't plug in. But here I have to plug in. So the numerator goes to 0 and the denominator goes to 0 because cosine 0 is 1, 1 minus 1 is 0. And this is lovely. I don't have to do anything. Just continue with L'Hopital's rule directly. So the numerator will be 2x, and the denominator is cosine prime is negative sign with minus in front, it's sine x. Now when I plug it in again, I know I get 0 over 0. But now remember, we had that limit Anyone remembers what would the answer be here? Either sine over or this over sine. What is the answer? Always.
Is answer 1?
Yes. Look, can I do this? No. I mean, should I? Or it's up to you. But since this approaches 0, I know that this limit approaches 1, as you already told me. Even if it's 0 over 0, there is no need for L'Hopital's rule here. What is the answer?
2?
That's it. Can you continue with L'Hopital's rule? Yes. And you get 2 over cosine, you still get 2. But why? If I have this tool, as long as it works, yes, it does. They're all the same and they approach 0. Now, if I have x approaches 1 or 5 or 10 or whatever, no, the answer is not going to be that.
So if we did either or?
It doesn't matter. It's up to you. It's
Okay.
up to you. It's up to you. Good.
I'm sorry, can you explain that as whatever x approaches the bottom part?
Yeah, we discussed this in chapter 3. This was our discussion from chapter 3. This was a limit that we analyzed, and I think we even looked at the graph. So if all these are the same, the answer is 1. And since we know the result, we can use it. It's highly recommended. Now, if you don't remember this, then you can have to continue with L'Hopital's rule and you still get the same thing. Is that okay?
Yes.
Perfect. Okay, do we want to choose anything else? So let me share my screen. Where is my button? Okay, got it. So let's see if we want to look at something else. So for example, if we look at 17, so we have limit as x approaches 1 from sine x minus 1 over x to the third plus x minus 2. Yeah, we plug it in, and it's 0 over 0. Lovely. So this is limit as x approaches 1. The numerator is cosine of x minus 1 times the inner function prime, but that's 1. The denominator is 3x squared plus 1. And now when you plug again, you have cosine 0, which is 1. And this is 3 plus 1, which is 4. So the answer is 1/4 on this limit. Any questions on 17? Okay. Let's see if we want to choose something else. For example, on this one, you probably could use L'Hopital's rule, but maybe I would have tried what? If you don't use L'Hopital's rule, what do we try on 25? Anyone? What method did we apply before L'Hopital's rule on a problem like this one?
Is it log?
No. Something else we did. Okay, let me copy it. So limit as x approaches 0, the square root of 1 plus 2x minus the square root of 1 minus 4x divided by x. Anyone remembers what we did before we studied L'Hopital's rule on this one?
I just can't remember what it's called, but
Yes,
we would
rationalize the numerator. Okay. Now let's see how this works with L'Hopital's rule. Let's see. First of all, I have to check. I cannot apply L'Hopital's rule just because, right? This is 1, this is 1, 1 minus 1 is 0, and this is 0. Okay, so let's see how this works. Limit as x approaches 0. The denominator is 1. Now when I differentiate this, I get 1 over 2 the square root of 1 plus 2x, but then times the inner function prime, minus 1 over 2 the square root of 1 minus 4x times the inner function prime. Okay, it's pretty nice. Not too bad. So these two go away. When I plug in 0 here, I have 1 over 1 minus. Here, this will be plus, and I simplify, and I get a 2, and this is 1. So this is plus 2, which is 3. Just quite easy. Wasn't bad at all. I would say even it's easier than rationalizing the numerator. So again, I plugged in 0. That's why the limit operator disappears now. When I plug in 0, I have 1 over 1. These two negatives change into positive. When I plug in 0 here, I have 1 in the denominator and 4 over 2. So 4 over 2 is 2. So that's why 1 from here and 2 from here, we get 3. Easier than rationalizing. It's less writing. Good. Do we want to choose anything else? Anyone else?
Can we do one that approaches infinity again?
You mean a power?
Yeah, power one.
A power,
one,
sure. Yes. So the powers are here. These are the powers. We did this. We did this, I think. It was on a homework, but we did it in class. So you choose. I think we did 67. You choose among any power. The ones with the power. 60 may be interesting. It has that little a in there. Of course, the a is a constant. And of course, that little b is a constant. Now you choose. It's up to you.
What about 68?
68. This one. Okay, perfect. I'm on page 8. Let's look at 68. And 68, we have limit. As x approaches 0, we have cosine x and 1 over x squared. Perfect. Great. Good. So first we have to plug it in. Where is cosine going? When x approaches 0. Careful, when x approaches 0, cosine is going to anyone? Anyone, please?
1.
Good. And where is 1 over x squared going?
Define.
0.
Careful. So let's discuss this. Yes. So 1 over x has this graph. But 1 over x squared has this graph. So where is it going again?
Infinity.
Yes. So we have this situation, unpleasant, but it is what it is. This is a long procedure. We have y cosine x to 1 over x squared. We have natural log y, 1 over x squared, natural log of cosine x. And now we have to apply the limit as x approaches 0 from natural log y, or limit as x approaches 0 from natural log of cosine x over x squared. Now, the denominator is going to 0. Where is the numerator going? Sorry.